Good day, viewers. Welcome to our today's class. We are still on thermodynamic relations. In today's lecture, we are going to be deriving the third TDS equation, and also we are going to be showing that the TDS equation, which is this, can be rewritten as this. So now, let's proceed. First thing first, we are going to be letting S, which is entropy, to be equal to function of pressure and volume. We let S to be equal to a function of pressure and volume. Now, if we do this from our fundamentals of partial derivative, of which we have been doing in our previous lecture, the S, we can say that the S from this equation will be equal to the partial derivative of S all over the partial derivative of P, keeping V constant, the P, plus the partial derivative of S all over the partial derivative of V, keeping P constant, the V. Now, this is what we have. This is what we have. Now, from this, what you can see on the board, I can decide to multiply this equation by T, both the left hand side and the right hand side by T. If I do that, I'll be having T ds to be equal to T into the partial derivative of S all over the partial derivative of P, keeping V constant, the P, plus T into the partial derivative of S all over the partial derivative of V, keeping P constant, the V. Next, I can rewrite these two terms. If I write these two terms, I'm going to have TdS to be equal to T into, now for this term, I'm going to have the partial derivative of S all over the partial derivative of T, keeping V constant, multiplied by the partial derivative of T all over the partial derivative of P, keeping V constant, the P, plus T into the partial derivative of S all over the partial derivative of T, keeping P constant, multiplied by the partial derivative of T all over the partial derivative of V, keeping P constant, dV. Now, this is what I'm going to have. What I've just done here is very simple. If I divide from here, you can see that the partial derivative of T can cancel out the partial derivative of T. I'll be left with this and this, which is equal to this. So from we can say that this term that I've just expanded is equal to this. Similar with this, partial derivative of T and the partial derivative of T can cancel out. I will be left with the partial derivative of S, which is this, all over the partial derivative of V, which is this, keeping P constant with V. So that is that. Now, if you remember from our previous lecture, we have proven that CV is equal to T into the partial derivative of S all over the partial derivative of T, keeping V constant. Also, Cp is equal to the T into the partial derivative of S all over the partial derivative of T, keeping P constant. You can see that we have Cv, its value is in this equation. We also have the value of Cp, which is this, in this equation. Therefore, I can substitute this for Cp. I can also substitute this for Cv. If I do this, this TdS equation will become TdS will now be equal to TdS will be equal to Cv. In place of this, I'm going to have Cv into this, which is the partial derivative of T all over the partial derivative of P, keeping V constant, dP, plus, instead of this, in place of this rather, I'm going to be putting Cp. I have Cp here. Then this, which is the partial derivative of T all over the partial derivative of V, keeping P constant, dV, keeping P constant, dV. So this is what I have. This is what I have. Now from here, you can see that I've successfully gotten my third TDS equation. This is my third TDS equation. Now, we are told that we should show that the third TDS equation after derivation is equal to this. Yes, it's equal to this. Now, how do we do this? Let's go. So from here, from these two equations, we are going to be making use of our PVT relation in order to show that this can be written as this. We are going to be making use of our PVT relation. Now, for PVT relation, of course, we are going to be using the cyclic relation for PVT, and it has been derived in our previous video. So I'm also going to be writing that relation. It states that the partial derivative of V all over the partial derivative of T, keeping P constant, is multiplying the partial derivative of T all over the partial derivative of P, keeping V constant, is also multiplying the partial derivative of P all over the partial derivative of V, keeping T constant. Everything is equal to -1. So this is the cyclic relation for PVT relation. This is the cyclic relation for PVT. Now, I'm going to be making the partial derivative of T all over the partial derivative of P, keeping V constant, the subject of this relation. Yes, that's what I'm going to be doing. That's what I'm going to be doing. If I do that, I'm going to have the partial derivative of T all over the partial derivative of P, keeping V constant, to be equal to -1 all over the partial derivative of V all over the partial derivative of T, keeping P constant, multiplying partial derivative of P all over the partial derivative of V, keeping T constant. I've just divided both sides of this equation by this and this, of course. So this and this will go from here, but they will appear under -1. So what's the next thing I'm going to do? I can take the inverse of this. This equation will become the partial derivative of T all over the partial derivative of P, keeping V constant. It will be equal to minus partial derivative of V all over the partial derivative to be the partial derivative of T. Here is going to be the partial derivative of T, and here, since I'm taking the inverse, we're going to have the partial derivative of V here, multiplied by the partial derivative of V all over the partial derivative of P in T constant. And this is what we have. Now, in order to move further, we are going to be making use of our compressibility factor and our coefficient of volume expansion. Now, I said coefficient of volume expansion beta, don't forget, is equal to 1 all over V. We have 1 all over V into the partial derivative of V all over the partial derivative of T, keeping P constant. We need to have this in mind, and also we need to know that K equal to -1 all over V into what? Into the partial derivative of V all over the partial derivative of P, keeping T constant. Now, in order to proceed, we need to have these two equations in mind. So next, let's screen this side as we proceed. Next, what are we going to be doing? I'm going to make this subject of this relation. I'm going to be making this the subject of this relation, and also this the subject of this relation. In order to move further, what am I going to do? From here, I'm going to be making, first I'm going to be taking the inverse of this equation. Before I do that, I can multiply both sides by the partial by V. If I do that, I will have V multiplied by beta to be equal to, of course, if V multiply this, it's going to cancel this, and that is gone. We have the partial derivative of V all over the partial derivative of T, keeping P constant. Next, I'm going to be taking the inverse of this equation. If I take the inverse of this equation, I'm going to have 1 all over V beta to be equal to partial derivative of T all over the partial derivative of V, keeping P constant. This is what I have. Next, I'm going to be coming back to my compressibility factor. What am I going to do here? First, I'm going to be multiplying both sides by minus V. If I multiply both sides by minus V, I'm going to have minus Vk, which as well can be called copper, but we're using K for the purpose of this class. We have minus Vk is equal to the partial derivative of v all over the partial derivative of p keeping t constant. Now this is what we have. Now come back to our equation. We have the partial derivative of t all over the partial derivative of v keeping p constant. It is here and it is equal to 1 over beta. We have the partial derivative of v all over the partial derivative of p keeping t constant. Of course, it is here, and it is equal to minus vk. So we are just going to substituting their values in this equation. If we do that, we are going to have the bracket of the partial derivative of t all over of v rather all over t p constant, partial derivative of t all over the partial derivative of p keeping v constant, of the partial derivative of t all over the partial derivative of p, yes, keeping v constant. This will be equal to, in place of this, we are going to put this. So we have minus, come first, into 1 all over v beta. We close our bracket. In place of this, which is this, we are going to put this, have the bracket of minus v. So this is what we have. So if we multiply, minus multiply by minus is plus, we are going to have vk all over vb. And of course, you know that v can go with v. We have minus going with minus, we have v going with v. This implies that this equation will now become the partial derivative of t all over the partial derivative of p, keeping v constant, will be equal to nothing but k all over b. This is what we have. Nothing but k all over b. Now, don't forget that we are asked to show that the TDS equation we just proved is nothing but this. That is, it can be written as this. Now, from here, you can see that this TDS equation, for this TDS equation, we can substitute this, of course, is this. We can substitute this, which is this, as this in this TDS equation. But before we do that, let's look for our other relation. Let's look for our other relation. Now, we know that 1 all over v beta is equal to the partial derivative of t all over the partial derivative of v keeping p constant. Also here, we know that this value is equal to this. So we can rewrite this TDS equation. TDS now will be equal to, we have Cp, Cv rather. In place of this, we are going to put in this value, because what is here is the same thing as what is here and it's equal to this. So we are going to have k all over beta. This is what we have. We have the p plus we have Cp. Now, in place of this, that is the partial derivative of t all over the partial derivative of v keeping p constant, we are going to be putting 1 all over v beta, because of course they are equal. So if we do that, we are going to have 1 all over v beta, and we have the v. So this is what we have. So finally, I can say that my TDS equation equal to Cv multiplied by k all over beta dp plus Cp all over, I'm going to have Cp all over v beta dv, and this is what I have. Now you can see that this Maxwell equation has been shown to be equal to what is here. Of course, what is here is equal to what is here. So we have derived the TDS equation successfully, and we have also shown that it can be written as this, which is this. So we have derived our equations. Now, thank you for watching. Be sure to like our video on our channel. You can subscribe to our YouTube channel as well. The link to our WhatsApp group is on the description. You can tap to join, and you are going to learn numerous relations and provings. Thank you for watching, and stay tuned for more videos.